Here's Professor Berkler back to talk about applications of transistors. In the previous video, we learned about the amplifying model and the switch model for a transistor. We also learned about BJT transistors, MOSFET transistors. And so I'm trying to create a Venn diagram here to kind of show you that there are differences between all these, but we can make amplifying circuits with MOSFETs. We can make switch circuits with BJTs, but oftentimes you'll see MOSFETs more being used in the digital world, the world of binary numbers, in the switch model world. And you'll see BJTs tend to be used for analog situations where we're wanting to amplify currents, but they can both be used in the other situation too. So examples of amplified current would be speakers, op amps, analog radios, and some examples of the digital world or worlds using the switch model would be voltage converters, motor controllers, integrated circuits, and logic gates. And we'll talk a little bit about logic gates in the next module. Okay, first we'll look at an example of a circuit that amplifies the current. So we have a BJT here. So we're going to use that equivalent model of a dependent current source here. Okay. So turns out that this current right here is beta IB. Where IB is over here. So let's start by figuring out what IB is in this case. So IB is equal to VN minus VBE. And VBE just means the voltage between the base and the emitter. And normally for a standard BJT architecture, that would be 0.7 volts. We divide all this by RS using Ohm's law. So if VN is much greater than VBE, right? If I'm like 15 volts, 0.7 is a very small amount of that. I might approximate this as VN over RS. Okay. And so how does V out relate to this IB? Well, let's see. We're just measuring voltage here, so no current flows. So that means that beta IB is flowing through the load resistor there. So V out is equal to beta IB times RL. So if I combine both of these equations together, then I get that V out is equal to beta V in over RS times RL. So if we assume RL and RS are the same, so if RL is equal to RS, then we can simplify this to V out is equal to beta V in. And beta is usually somewhere between like 50 and 1,000. So we're having a pretty large increase in voltage caused by the amplifying of the current. Now, what's going to limit the voltage in the circuit? Our power supply over here, right? So at some point, we're going to saturate if our output voltage down here starts getting near our power supply amount. So there are edge cases here. We can't just keep infinitely amplifying. Now we will look at an example of a voltage-controlled switch. This is from pictures from Technology Brief 10. So if this interests you, go read that technology brief. And this opens the whole world of digital design, digital circuits. So you would want to take ECE 3700 if this is of interest to you. So let's start by relabeling these nodal voltages. This might help some of you by having them actually marked as input voltage sources. And VDD is just a term they commonly use in the digital world to represent their positive power supply. Okay, so in the circuit here, since we're in the digital world, we're thinking about applying zeros or ones, logical zeros or ones. So 0 is represented by 0 volts, 1 is represented by maybe 5 volts, and maybe VDD is also 5 volts in this case. Great. So if we apply 1 volt, or sorry, logical 1 or 5 volts over here, that will turn on the transistor, in the case of this NMOS transistor here. And it has some small resistance, like 0.1 ohm. Since that's a lot smaller than R, I'm just going to approximate it as a wire. So then in this case, V bit is now directly connected to ground, and current can flow because remember, grounds are all connected here. So current can flow like this, and V bit's connected to ground now. So V bit is then equal to 0 volts in this case. So that was kind of interesting that this switch is kind of backward logic. I apply a voltage, and then suddenly I get no voltage over here. And the opposite is true when if I apply 0 volts here, then this switch is not on. So there's no connection for current to flow, and thus no current flowing here means no voltage drop across the resistor. So then this becomes 5 volts. So I could basically have an opposite logic going on here, where I put in a high voltage, get out a low voltage, put in a low voltage, get out a high voltage. So let's go look at how actual modern computers implement this. So CMOS stands for complementary MOSFET logic. And it's called complementary because we have both flavors of MOSFETs, the PMOS and the NMOS. And so let's see what this circuit does. So I can input, again, using this whole idea of binary, I can input a 0, a logical 0, or a logical 1. A logical 1 will be 5 volts. And then let's look at what we get out in each case. So in the case that we put in 0 volts here, then this one is not on, no connection down to ground here. And 0 volts on the PMOS will actually turn this one on. So we get a wire connecting here essentially. So I can say that out is equal to VDD, which is, we're assuming this is all a 5 volt system. So 5 volts. And now what if I put 5 volts here instead? Okay, so in that case, this transistor turns off, so no connection. And 5 volts turns this one on, so now we connect to ground. So this is doing basically the same thing as the last circuit, right? We're turning a 0 volt into a 5 volt, so a off logic into an on at the output, and an on or a 5 volt into a 0 volt or an off. So this is called an inverter. This would also implement a not logic gate. And the reason we use 2 transistors like this instead of a resistor and a transistor is that we have less power loss over in this situation. So again, if this interests you, please go and take ECE 3700.